Hello and welcome to this video. So today we will discuss about liquid helium and its applications, and who this person is, that also you'll understand. Okay, so what is liquid helium? So we know that helium is a gas, and helium is one of the lightest elements that is available. So when this gaseous helium is liquefied at a very low temperature, then it becomes liquid helium. So in helium, the intermolecular attractions are so weak that it remains as a gas up to 4.2 Kelvin of temperature. That I will discuss in a while with a phase diagram. But up to 4.2 Kelvin of temperature, gaseous helium exists as a gas, and then below that temperature there is a phase transition and it becomes liquid helium. And it is one of the coldest substances. Of course, in order to helium exist as a liquid, it has to be cooled below 4.2 Kelvin temperature. So you can understand what it will be, a very cold substance, right? Even at 0 degrees Celsius, when water is condensed to ice, 0 degrees Celsius, that means 273 Kelvin. If 273 Kelvin means that is the temperature of ice, then 4.2 Kelvin, which is 269 Kelvin below 273 Kelvin, so it will be very cold. And that is why this liquid helium is like stored in a very specialized container, okay, and which has been shown here. So these are liquid helium containers, and that is why, because it's very cold, so you cannot keep them in normal temperature. You can't store them at normal air temperature, so they are stored in such specialized vessels. Okay, so it is very useful, in fact, and that is why we are discussing about liquid helium today. Its application also we will understand. Okay, so what are the basic properties of liquid helium? Okay, so the boiling point is 4.2 Kelvin temperature. Boiling point means, so helium is a gas, okay, and so at helium is a gas up to 4.2 Kelvin temperature. I mean, at 4.2 Kelvin temperature and above it, this liquid helium will become gaseous helium, and at 4.2 Kelvin and below it, the gaseous helium will become liquid helium. Okay, so the temperature is around minus 269 degrees Celsius. So minus 269 degrees Celsius. So you can understand how cold it will be. Okay, so it's colorless. It has no color. It's odorless. No odor. It's chemically inert. Okay, helium is a noble gas, and that is one of the reasons why helium is used in cryogenics. Cryogenics means the physics of low temperatures as opposed to hydrogen, because hydrogen is very reactive. Now, superfluidity. Helium has a very special property of superfluidity, that also I will discuss in the phase diagram. So below 2.17 Kelvin temperature, helium-4 becomes superfluid. Superfluid means it is a fluid which has zero viscosity or which can flow without friction. Okay, so superfluidity is equivalent to superconductivity in solid. Okay, in solid we call superconductivity, and in liquid we call it superfluidity, because a superconductor means no resistance. In superfluid means there is no viscosity. Okay, so remember the temperature. Okay, so now the question is, who liquefied helium? Helium was first liquefied by this professor, this scientist. His name is Heike Kamerlingh Onnes. He was a Dutch scientist. He did it on July 10th, 1908. He was a professor at Leiden University in the Netherlands, and he was the first person who liquefied helium gas by cooling it to 4.2 Kelvin. Okay, let me give here an example. Water is liquefied between 0 degrees Celsius and 100 degrees Celsius. So if steam is there, water vapor, if you can cool it down below 100 degrees Celsius, then it will become liquid water. Okay, so compared to that temperature, you see this temperature of liquid helium is so small, only 4.2 Kelvin. It is at near 0 Kelvin temperature. Okay, so how he achieved this? He used advanced cryogenic techniques by compressing the gas and by Joule-Thomson effect. Okay, what is Joule-Thomson effect? I will discuss it maybe in a future video, but this is how he converted gaseous helium into liquid helium. So now let us understand the phase diagram, then a lot of things will be clear to you. So this is the phase diagram of helium. So along the x-axis we have temperature in Kelvin scale. Along the y-axis we have pressure measured in bar. Okay. So this particular red line is called lambda line. Okay. So why lambda line? I will discuss it in a future video. But before that, I will discuss another video which will be first and second order phase transition. Okay. After we learn about first and second order phase transition, then I will discuss about the lambda graph, and then you will understand what this lambda line is or why it is called a lambda line. So that I'll save for another video. Okay, so now let us understand the various phases. Okay, so 4.2 Kelvin temperature. Okay, this is 4.5. So here it is 4.2 Kelvin. Below this 4.2 Kelvin, helium becomes a liquid. Okay, and it remains so up to near 0 Kelvin temperature. So helium 1 and helium 2. So what is helium 1? Helium 1 is normal liquid. Helium 2 is superfluid. So here where this red line has met this temperature axis at this particular point, which is 2.17 Kelvin. So below 2.17 Kelvin, helium becomes a superfluid. Okay, zero viscosity, and above 2.17 it is liquid. Okay, and boiling point is 4.2 Kelvin. So the vapor pressure graph you see above this temperature, so helium becomes a gas. So not only that, helium can also be converted into a solid. How? If you cool down sufficiently below 2.17 Kelvin, near 1 Kelvin, and so, and if you can apply a very high pressure of 25 bars, very high pressure. Okay, at atmospheric pressure it will never become solid, it will just become a liquid. But you can also convert helium into a solid provided you apply a very high pressure of 25 bars. Okay, this melting curve you see, beyond this melting curve helium exists as a liquid, and to the left it exists as a solid. So this is the phase diagram of helium 4. Remember, helium 1 is the normal helium, helium 2 is the superfluid helium. Okay, so applications, in brief I will discuss the applications. So superconducting magnet. So in MRI machines in hospitals, okay, helium 4 is used. In particle accelerators like the LHC in CERN, so helium 4 is used to cool down magnets to superconducting states. Cryogenics means low temperature physics. Fundamental research in low temperature physics, helium 4 is widely used, which maintains, so for certain experiments you have to use ultra cold environment. Okay, that is why in those cases also helium 4 is used. Quantum computing, in quantum computing, so it cools down the qubits, okay, so that they can function near absolute zero. Why? Because if the temperature is very high, there will be no quantum entanglement. So quantum computing is another huge topic of which can be discussed. So in future maybe I will discuss this topic separately, but for today, in quantum, you understand that in quantum computing also liquid helium is used to maintain quantum entanglement. Space exploration, okay, to cool down the instruments and the fuel in satellites and spacecraft, because the fuel may get very hot, and in order to cool down the fuel it has to be cooled down using liquid helium. Then in NMR spectroscopy, for analyzing nuclear magnetic resonance spectroscopy is used to analyze molecular structure, and in that case also liquid helium is used in this particular instrument. However, there are certain challenges. So it is non-renewable. Once released, it escapes into space because it is very light, so it will easily escape into space. So there is global shortage because it has huge demand but limited supply, and it is also expensive. Cooling down gaseous helium to liquid state is very expensive. You need state-of-the-art laboratory systems on laboratories in order to cool down gaseous helium. Okay, liquefaction costs are very high. These are some of the challenges. So friends, we have discussed today about liquid helium and its applications. So it has numerous applications, and some of these applications I will discuss in future, including superconductivity. And the phase diagram also, we have discussed today. So another aspect of the phase diagram will be discussed in future. So when we'll understand more about the phase transition of liquid helium, but before that I will make a video on phase transition in materials. So friends, thank you very much for watching this video. I hope you have found this useful. Please like, share and subscribe to this channel. I will soon see you with another such very interesting video. Thank you very much.